It's August 7th, 2026. Hope you're doing great wherever you're watching from. So there is something genuinely strange happening underneath the ground in Northern California right now. And I don't mean that in a dramatic clickbait kind of way. I mean scientists with actual seismometers, actual satellites, and actual peer-reviewed papers are telling us that the picture we thought we understood about what's under that stretch of coastline is wrong. Not slightly wrong, fundamentally wrong. For decades, geologists taught that 3 tectonic plates meet off the coast near Humboldt County, and everything from earthquake hazard maps to emergency planning got built around that 3-plate model. Well, that model just got torn up. A study published this year in the journal Science found that there aren't 3 moving pieces under Northern California. There are 5. 2 of them were completely hidden, buried, undetectable, until researchers figured out how to listen for earthquakes so small that no human being could ever feel them. And while that discovery was still making headlines in scientific circles, the ground actually moved. In June, a magnitude 5.6 earthquake ripped through a fault near Ukiah that wasn't even considered particularly dangerous. Just weeks after that, a swarm of small quakes started rattling a Bay Area suburb that has no business having that many earthquakes. And this week, new satellite data confirmed that a chunk of land east of the Sierra Nevada, sitting on top of one of the largest volcanic craters in North America, has been steadily rising for almost 50 years, and it just won't stop. So today, we're going to dig into all of it in detail. We're going to talk about the hidden slab of rock scientists just found underneath the coast. We're going to talk about the earthquake that broke a record on a fault nobody was watching closely. We're going to talk about the swarm outside San Francisco that had residents feeling like they were living on a trampoline. And then we're going to go all the way through the 7 volcanoes sitting quietly under California, with molten rock underneath them right now. And by the end, you'll understand why scientists are being extremely careful with their words, because careful is exactly what you have to be when you're talking about something this complicated and this potentially serious. So let's rewind, because to understand why this year's discoveries matter, you have to understand what scientists thought was going on before. And honestly, you have to understand just how long this particular puzzle has been sitting unsolved. For a long time, the story of Northern California's geology was told through a single meeting point, the Mendocino Triple Junction, sitting just offshore from Humboldt County. Picture it like a geological intersection where 3 massive slabs of the Earth's crust bump into each other, except unlike a normal intersection, none of these slabs ever stop moving. South of that junction, the Pacific Plate grinds northwest against the North American Plate, and that grinding motion is what creates the San Andreas Fault, the fault most people associate with California earthquakes because of its reputation in the Bay Area and its long-standing association with the so-called Big One. North of that junction, a smaller plate called the Gorda Plate, sometimes lumped in with the larger Juan de Fuca Plate to its north, is doing something completely different. It's diving underneath the North American Plate in a process called subduction, sliding down into the mantle like a conveyor belt heading straight into a furnace. That's the Cascadia subduction zone, and it's the same fault system responsible for the chain of volcanoes running up through Oregon and Washington. It's capable of producing the kind of magnitude 9 earthquake that reshapes coastlines and sends tsunamis rolling across the entire Pacific Basin. For years, this 3-plate picture seemed to explain most of what scientists observed, and honestly, it's a reasonably intuitive model. 3 big slabs, 1 triangle-shaped meeting point, clean and tidy. But there was always one nagging problem sitting in the data. In 1992, a magnitude 7, 2 earthquake hit near Cape Mendocino, and it struck at a depth that simply didn't fit. Scientists had assumed that if you're dealing with a subducting slab, the fault should track along its leading edge as it dives deeper into the earth, meaning ruptures close to the trench should occur at a predictable depth. But the 1992 quake broke way shallower than that logic predicted, and for over 3 decades, that mismatch just sat there as an open question. One of those nagging details that didn't quite fit the tidy model, filed away in the back of everyone's mind because nobody had a better explanation to offer. Then earlier this year, a team from the U.S. Geological Survey, UC Davis, and the University of Colorado Boulder published a paper in Science that finally cracked it open. Their method was clever, and honestly, it's worth walking through because it tells you a lot about how far earthquake science has come. Instead of relying only on earthquakes big enough for a person to feel, they went hunting for something called low-frequency earthquakes, tiny slip events that happen when tectonic plates slide against each other extremely slowly, almost imperceptibly. These things are thousands of times weaker than anything you or I could ever notice standing on the surface, but a dense network of seismometers scattered across the Pacific Northwest was sensitive enough to pick them up, one after another, building up an enormous catalog of these micro-events over time. And here's the genuinely clever part. The researchers checked whether these tiny quakes responded to tidal forces, because just like the gravitational pull of the sun and moon tugs on the ocean to create tides, that same pull places a subtle rhythmic stress on tectonic plates deep underground. When that tidal stress happens to line up with the natural direction a fault wants to slip, you get a measurable uptick in the number of these tiny quakes. When the tidal stress points the wrong way, you get fewer. By carefully mapping which tiny quakes responded to which tidal directions, and cross-referencing that against thousands of data points, the team could effectively reconstruct the shape, depth, and orientation of faults that are completely invisible at the surface, the same way you might infer the shape of a hidden object by watching how it deflects light you can't directly see. One of the lead researchers compared the whole challenge to studying an iceberg. You can see a little bit poking up above the waterline, but the real shape and mass sits hidden below, and you have to reconstruct it indirectly using whatever clues filter up. What they found rewrote the map entirely. At the southern end of the Cascadia subduction zone, it turns out a piece of the North American plate itself has broken away from the rest of the continent and is being dragged downward alongside the Gorda plate as it sinks into the mantle. That's the first hidden piece. And separately, south of the Triple Junction, the Pacific plate is dragging a slab of ancient crust called the Pioneer fragment underneath the North American plate as it continues its northward march. This fragment is essentially an orphaned piece of the old Farallon plate, an ancient tectonic plate that used to run the entire length of the California coastline millions of years ago and has mostly been swallowed whole by subduction over time, leaving only scattered remnants like this one behind. The fault separating this Pioneer fragment from the rest of the North American plate lies almost completely flat, which is exactly why nobody could see it before. It simply doesn't create the kind of steep, obvious boundary that shows up clearly using older surveying and mapping methods. So instead of 3 plates meeting neatly in a triangle, you've actually got 5 moving pieces jammed together in a tangled knot, 2 of them buried and previously invisible. And this new geometry finally explains why that 1992 earthquake broke so unexpectedly shallow. The surface being pushed underneath North America simply isn't as deep as everyone assumed for 30 years, and the plate boundary isn't sitting where the textbooks confidently told us it was. Now, why does any of this actually matter beyond just being a fascinating academic discovery? Because earthquake hazard models are built entirely on exactly this kind of structural information. If you don't know the true shape, depth, and orientation of the faults underneath a region, you genuinely cannot accurately estimate how big a future earthquake could be, how far the shaking would travel, or which communities are sitting in the highest risk zones. This is the kind of foundational correction that ripples outward through every seismic hazard map, every building code recommendation, every emergency planning document written for that stretch of coast. It's not just an academic curiosity confined to a journal nobody outside the field will ever read. And it's definitely not just theoretical, because barely 5 months after that paper came out, the ground itself gave scientists a very real, very immediate demonstration of exactly why this update matters. On the morning of June 24th, a magnitude 5. 6 earthquakes struck near the small city of Ukiah, and it hit directly beneath a stretch of mountainous, forested terrain, close enough to a monastery in the area that it rattled the buildings there pretty severely. Seismometers within roughly 10 kilometers of the rupture recorded shaking intensities in the strong to severe range on the standard scale scientists use. Roughly 10,000 people experienced that kind of intense shaking directly, and more than 4,500 people filed reports online describing exactly what they felt, most of them further out where the shaking had naturally weakened with distance. An early warning alert did go out through the region's shake alert system, but for people right inside the zone of strongest shaking closest to the epicenter, it arrived too late. The ground was already moving hard by the time the notification actually reached their phones, which tells you something important and slightly humbling about the physical limits of these systems when an earthquake originates that close to the people it's trying to warn. But here's the detail that really caught researchers' attention and made this more than just another routine quake. The fault involved is called the Maacama Fault, and June 24th produced the largest earthquake ever recorded on it. Not the largest in years, not the largest this decade. The largest ever recorded, full stop. And when you look at the California Geological Survey's official fault and fold database, some of the fault traces running through that exact area are actually flagged as old, meaning pre-quaternary in geologic terms, essentially telling you these particular structures haven't been considered seismically active in an extremely long time, if ever, according to the maps. So when a fault labeled ancient and quiet suddenly produces its biggest recorded rupture in living memory, that is precisely the kind of anomaly that makes scientists sit up straight, because it strongly suggests our existing fault maps in that region might be missing something important, in much the same way the old 3-plate model was missing 2 entire tectonic fragments hiding in plain sight. And this wasn't an isolated blip either. Just weeks before that Ukiah quake, In the Bay Area city of San Ramon, residents started noticing something genuinely unusual. Not one earthquake, not two, but a swarm, a sustained sequence of small quakes hitting the same general area over and over again, day after day. If you've never personally experienced an earthquake swarm, it's a genuinely strange sensation. It's not the single sharp jolt most people picture when they think of an earthquake. It's this rolling, repeating unease, almost like the ground keeps clearing its throat every few hours. Now, earthquake swarms by themselves aren't automatically alarming. They happen periodically all across California without leading anywhere dramatic. But they matter, because swarms are one of the very first warning signs scientists look for when trying to figure out whether volcanic activity might be quietly involved somewhere nearby. When magma, gas, or superheated fluids start moving underground, they tend to crack surrounding rock as they push forward, generating exactly this kind of clustered, repetitive seismic pattern rather than one clean main shock followed by a gradually fading sequence of aftershocks. So naturally, when San Ramon started shaking again and again, people online started asking the obvious question almost immediately. Is there a volcano hiding under the Bay Area that nobody bothered to mention? And this is honestly a great moment to pause and give you the actual diagnostic tool scientists use to answer that exact question, because it's genuinely useful, it's not overly complicated, and it applies everywhere, not just in California. There are two main things you look at to tell a tectonic swarm apart from a volcanic one. First, you look closely at how the earthquakes behave over time. Volcanic swarms caused by magma or hydrothermal fluid movement usually don't follow a clean, predictable decay pattern the way a normal aftershock sequence does. Instead, they tend to arrive in bursts and pulses, sometimes in an almost rhythmic drumbeat pattern as fluid repeatedly forces its way through cracked rock, again and again. Tectonic swarms, on the other hand, tend to follow more standard, textbook aftershock behavior. An initial dense cluster right after the triggering stress, which then gradually and predictably tapers off over days or weeks. Second, and just as important, you look at location relative to any known volcanic systems in the area. And this is exactly where the San Ramon story actually resolves itself pretty cleanly, because when USGS scientists mapped the swarm out on a satellite image, it sat well outside any recognized volcanic field in the region. The nearest volcanic areas, places like the Clear Lake Volcanic Field, Mount Shasta far to the north, and the long-dormant Berkeley Hills volcanics, were all a meaningful distance away from where the shaking was concentrated. So, despite the genuinely unsettling repetition residents felt, San Ramon's swarm ultimately got classified as ordinary tectonic stress relief along the dense fault network running through the East Bay, not a sign of rising magma underneath a major metro area. Good news, obviously, for the roughly 2.5 million people living in that broader region. But it's a perfect real-world illustration of exactly the kind of careful diagnostic thinking scientists have to apply constantly in a region this seismically busy, and it's exactly the kind of judgment call that gets meaningfully harder to make with total confidence when your underlying structural map of the crust just got quietly rewritten a few months earlier. Now let's talk about the third major piece of this puzzle, because unlike the sudden Ukiah quake or the short-lived San Ramon swarm, this one has been slowly building for almost 50 years, and it just got a fresh, very current update. East of the Sierra Nevada sits the Long Valley Caldera, a massive volcanic depression roughly 10 miles wide and 20 miles long, formed approximately 760,000 years ago by an eruption so violent it's officially classified as a super eruption. That eruption blew out somewhere around 150 cubic miles of magma from a depth of about 4 miles beneath the surface, and rapidly moving flows of glowing hot volcanic ash covered much of east central California, while airborne ash reportedly drifted as far away as present-day Nebraska. The ground above the emptied magma chamber then collapsed by more than a mile, forming the enormous caldera we can still see today. For most of its recent history since that catastrophic eruption, Long Valley has just sat there quietly, hosting hot springs, fumaroles, and eventually the ski resort community of Mammoth Lakes, which now sits right on its southwestern edge. But starting in 1978, after decades of relative stability, geologists began noticing that the ground in the center of the caldera was rising, slowly, steadily, in a dome-like pattern centered directly over the middle Pleistocene resurgent dome. By the early 2000s, that resurgent dome had climbed nearly 2.5 feet, and the deformation had spread across more than 100 square miles of surrounding terrain. And as of new geodetic survey work released just this year, the caldera has continued that same slow bulging pattern, with total uplift since 1978 still sitting right around that same 2.5-foot mark, rising in distinct episodes rather than one smooth, continuous climb, swelling noticeably for a while, then pausing and going quiet for years, then stirring back to life again later. Here's where it gets genuinely interesting, though, because scientists are still actively debating exactly what's driving that uplift. And the two leading theories tell fairly different stories about how worried you should be. One camp argues this is being driven by fresh magma physically intruding into the upper crust from deeper down, pushing the ground up the same way a balloon rises as you steadily fill it with air. But another line of research, using 100 kilometers of buried fiber optic cable laid across the caldera and essentially repurposed into a giant distributed seismic sensor array, found something more nuanced. Their subsurface imaging showed a clear, well-defined separation between the shallow hydrothermal system near the surface and the actual magma chamber itself, which sits much deeper than a lot of earlier estimates assumed, around 12 kilometers down. And what they found supports what researchers call the second boiling hypothesis. Basically, the idea here is that the enormous rhyolitic magma reservoir left behind by that ancient super eruption has been slowly crystallizing for hundreds of thousands of years, essentially cooling and solidifying from the outside in, and as magma crystallizes, it releases trapped water and gas that were originally dissolved within it, kind of like how ice cubes push mineral impurities out toward the surface as they freeze solid. Those released fluids build up significant pressure underground and push upward through the overlying rock, causing the uplift and triggering the associated earthquake swarms, without requiring any genuinely fresh molten rock to actually be rising from much greater depth. It's a subtle distinction on paper, but it matters enormously for how concerned you should realistically be, because fluid-driven unrest and fresh magma-driven unrest carry meaningfully different implications for near-term eruption risk. And notably, researchers found that the area sitting right beneath most of the resurgent dome itself actually shows very little seismicity at any depth, essentially no emission of magmatic gases like carbon dioxide, and only normal to slightly below normal heat flow readings, all of which points further toward the fluid explanation rather than genuinely fresh magma actively rising toward the surface. Interestingly, researchers also found that since 1980, the seismic energy released along the broader Sierran fault zone adjacent to the caldera has actually been several times greater than the energy released along the caldera's own ring fault zone. A reminder that a meaningful chunk of what people attribute to the caldera acting up is really regional tectonic stress happening right next door to it, not necessarily the volcanic system itself. All right, before we get further into the volcanic side of this story, let's take a quick breather, because this is exactly the kind of story that genuinely benefits from more eyes on it and more informed conversation, rather than getting reduced to a scary headline nobody actually reads past. If you're finding this rundown useful so far, go ahead and hit that like button. Drop a comment telling me which part surprised you most, whether it's the 2 hidden tectonic fragments nobody knew existed, the record-breaking Ukiah quake on a fault that was supposedly ancient history, or a caldera that's been quietly rising since roughly the era of disco and still hasn't fully settled down. And if you know someone who lives anywhere near Northern California, or honestly anyone who's just into this kind of science, send this their way, because understanding what's actually happening under your feet beats doom scrolling through panicked headlines that never bother explaining the actual mechanics behind them. Subscribe if you want more of these deep dives as new research keeps dropping, because this particular story is very clearly still evolving in real time. Now, Long Valley isn't operating in isolation, and it's worth being thorough here rather than rushing past it because context matters. It's just one of 16 young volcanoes scattered across the state that the U.S. Geological Survey ranks somewhere between low threat and very high threat. And out of those 16, at least 7 currently, have actual molten rock sitting beneath them right now, actively producing some combination of volcanic earthquakes, toxic gas emissions, hot springs, or measurable ground deformation. So let's run through this list properly, one by one, because it paints a much fuller picture of exactly how much simmering geologic activity Northern and Central California are collectively sitting on top of, quietly, most of the time, without much sustained public attention outside of moments like this one. Start with Mount Shasta, up near the Oregon border, one of the most instantly recognizable peaks in the entire Cascade Range, a massive stratovolcano that dominates the horizon for miles and miles in every direction you look. Shasta is considered one of the higher threat volcanoes in the state, specifically because of its sheer size, its documented history of significant eruptions going back thousands of years, and its close proximity to populated communities and major transportation corridors running through the region. It hasn't erupted in centuries, but the magma system underneath it is still very much alive and monitored continuously for exactly the kind of seismic and deformation signals that would indicate it's starting to wake back up. Not far away sits Medicine Lake Volcano, which is actually the largest volcano by total volume anywhere in the Cascade Range, even though it doesn't have the single dramatic photogenic peak silhouette that makes Shasta so instantly recognizable from a distance. Instead, it's a broad, sprawling shield volcano covering an enormous footprint. And it hosts an extensive documented history of eruptions spread across a wide surrounding area, along with ongoing background seismicity that keeps it firmly on the active monitoring list year after year. Then there's the Lassen Volcanic Center, home to Lassen Peak, which actually erupted as recently as the early 20th century, making it the most recently active volcano in California, outside of the Long Valley volcanic region entirely. Lassen still produces plenty of visible geothermal features today: boiling mud pots, hissing steam vents, and sulfurous fumaroles that visitors can walk right up to and see firsthand in the national park built around it. Essentially visible daily proof that there is genuine heat sitting not particularly far below the surface in that part of the state. The Clear Lake Volcanic Field up in wine country north of San Francisco might honestly be the most underappreciated entry on this entire list, given how close it sits to a fairly dense population base. It's a broad field of scattered volcanic domes and craters rather than one single dominant peak, and it sits directly adjacent to Clear Lake itself, California's largest natural freshwater lake. Beneath it lies one of the most productive geothermal fields anywhere in the world, which is actually harnessed for real, functioning renewable power generation at a nearby geothermal complex, a rare case where all this simmering underground heat gets put directly to productive use, rather than just being passively monitored as a distant hazard. Further south and east, the Coso Volcanic Field sits out near a military testing range in a fairly remote stretch of desert, another site with a well-documented history of past eruptions and ongoing geothermal energy production, drawing on the same underlying heat source. And down near the Salton Sea, the Salton Buttes represent one of the more unusual volcanic features anywhere in the state, a cluster of small rhyolite domes that erupted in an area better known these days for its geothermal energy potential and its complicated ongoing environmental history surrounding the shrinking Salton Sea itself. And finally, tying everything back to where we started, there's Long Valley itself, along with the adjacent Monoino craters chain, which is technically distinct both chemically and tectonically from the main Long Valley magmatic system, even though it shares the same broader neighborhood and cuts right through the caldera's northwest rim. The most recent volcanic activity in that immediate area actually happened around Mono Lake roughly 300 years ago, which in geologic terms is basically yesterday afternoon. So when you step back and look at all 7 of these systems together as one connected picture, what you're really looking at is a state sitting directly on top of an enormous amount of stored geologic energy, some of it purely tectonic, grinding plates against each other along faults both old and newly discovered, and some of it genuinely magmatic, sitting in reservoirs that have been slowly cooling and crystallizing for hundreds of thousands of years. And the honest, unglamorous truth that responsible scientists keep emphasizing over and over again is that most of this activity does not lead to anything remotely catastrophic. Research on large calderas worldwide has consistently found that only about 1 in 6 episodes of measurable unrest actually culminates in an eruption of any size. Most of the time, the ground rises a little, the earthquakes swarm for a while, the fumaroles hiss a bit louder than usual, and then it all quietly settles back down, sometimes for decades at a stretch, before eventually stirring again years or generations later. But here's the honesty check, because I don't want to just wave all of this away as nothing to see here either. That wouldn't be fair to you or to the actual science. The reason this year's news genuinely matters isn't because any single event on its own, the Ukiah quake, the San Ramon swarm, the Long Valley uplift update, is individually alarming. It's the layering of all 3, combined with a genuine, formal scientific rewrite of the underlying structural map that should make you pay closer attention rather than simply tune it out as background noise. When researchers discover that 2 entire slabs of crust were sitting there completely undetected for decades, hidden because they lie flat and don't create obvious surface signatures, that tells you plainly that our tools have real limits and that the confidence people place in existing hazard maps needs to be paired with genuine humility about what we still don't fully know. It also directly explains why a fault flagged as ancient and inactive on official government maps can turn around and produce its largest recorded earthquake without much advance warning at all. The ground, quite simply, doesn't read the same maps we do. So here's the question nobody's really connecting yet, at least not loudly. If the newly discovered Pioneer fragment and the torn-away piece of the North American plate have been quietly reshaping stress patterns along that stretch of coast for who knows how long already, and if that reshaped stress is part of what's now waking up faults like the Maacama that geologists previously considered essentially dormant, then how confident can anyone actually be that we've mapped every single hidden structure feeding into this system? Because remember, this entire discovery only became possible once scientists figured out how to reliably listen for earthquakes thousands of times too small for any person to ever feel. That naturally raises an obvious follow-up question. What else might be sitting down there that we simply haven't developed the sensitivity to detect yet? And separately, on the volcanic side of things, if the leading hypothesis for Long Valley's uplift really is fluid release from a slowly crystallizing ancient magma chamber rather than genuinely fresh molten rock rising toward the surface, that's certainly more reassuring news than the alternative scenario, but it still means the entire system is actively venting real pressure inside a caldera, that was, at least once in its deep geologic past, capable of a full supereruption. Reassuring is simply not the same thing as inert. Put those two threads together, a tectonic structure proving far more complicated and far more hidden than anyone confidently realized, sitting right alongside a chain of 7 separate magma-fed volcanic systems that have all been quietly building and releasing pressure for decades in their own individual ways. And what you get is a region where the scientific humility on display this year is honestly the single most useful thing to come out of all of it. Nobody credible in this field is predicting some kind of imminent catastrophe here. But nobody credible is dismissing it as nothing either. What's actually happening beneath Northern California right now is scientists doing exactly what they're supposed to do when new evidence arrives, updating the underlying model the instant the data demands it, rather than clinging stubbornly to a comfortable old picture just because it was simpler to explain to the public. So I'll leave you with the same open question researchers themselves are genuinely sitting with right now. As monitoring technology keeps improving year after year, and as we keep uncovering entire structures and fragments that were completely invisible just a few years ago, do you think our current earthquake and volcano hazard maps for the West Coast are actually keeping pace with what's really happening down there? Or are we going to keep getting these kinds of surprising headline-making updates every few years, simply because the tools are only now catching up to the true complexity of the geology? Let me know what you honestly think in the comments below. I would genuinely love to hear your take on this one. If this rundown helped make sense of a pretty complicated, layered topic, go ahead and hit that like button, drop a comment with your thoughts, and share it with anyone you know who lives out west or who's just generally into this kind of science, and subscribe so you don't miss the next update as this developing story continues to unfold. Thanks so much for watching, guys.